Today we have another seminar that is related to smooth particle hydrodynamics. The speaker is Matteo Teodori from the University of Networks, and I will leave the audio to Michelangelo to introduce Matteo.
Okay. Thank you. Matteo stayed with us in 2022 from June to December, more or less, and now he's a PhD student at the University of Campania, in Givabitelli, in Caserta. He is working on tabular mass with N models, N-body models, essentially Lagrangian technique. He works with me, with Gianfranco, Cristina, and Luca on the developing of a code in SPH smoothed particle aerodynamics. And now he presents his main activity about the moon plumes and Enceladus plumes. And before he discuss more or less the main points of SPH techniques.
Okay, thank you, Michelangelo, for the introduction. Let me first thank all of you that I met more or less 2 years ago. And I would like to thank you for the support that you always give me, and the interaction with you is always good. I also want to thank the organizers for this opportunity. Today, as Michelangelo already said, I would like to outline you the approach we are using for studying volatile emission from planetary surfaces. That is called smoother particle hydrodynamics. You can find it both then in the acronym SPH. So let's see what SPH is. Generally speaking, it is a computational method designed for continuous media simulations in the Lagrangian description. So for those not familiar with computations, computational method generally is something that you compute with your computer. Typically, you solve equations. The continuous media is in the limit of continuous world. So you simulate, you imagine that the world is made of continuous stuff. And the Lagrangian acronym, let's say name, let's see what does it mean. So in physics, there is a formulation of classical mechanics that is based on the principle of least action. So once you have a Lagrangian function that describes your system, this principle requires that the temporal evolution occurs at the stationary points of the so-called actional function. This gives you the Lagrange equation, which are actually the equations of motion that are describing the evolution of your system. And typically, the Lagrangian approach is compared to the Eulerian one. So the Lagrangian approach, the observer is doing okay. When you and go down the river. When the Eulerian approach that is intrinsically based on fixed domain, you are focused on specific. Watch the fluid passing through, like on a bank of a river, and watch the water pass through that position. So, as I said, the Eulerian approach is intrinsically a grid-based method, while the Lagrangian approach is a particle-based method. So you actually work with fluid parcels, fluid elements that you call particles, and that describe and measure in a discrete way, of course, your continuous physical world. And those volume elements are actually macroscopic elements, so you can define macroscopic quantities and thermodynamic quantities. So imagine you have a cloud, and you simply split it into several particles. And so concerning smoothed particle dynamics, as we said, it is a computational method that uses the Lagrangian approach. And due to this fact, it has some advantages. First, it is mesh-free, so you do not require a grid to compute stuff. And this means that it is easier to implement and also to parallelize. But one of the most important things is that it is very good in following rapid variation of physical quantities. So you are able to consider larger boundaries. Again, since it comes from a Lagrangian, it has great conservation features. So you can derive all your equations from the SPH Lagrangian function. It has a large applicability. We are going to see this in the next few slides. And among the limitations, because every method has its limitation, I think that one is that the setting boundary conditions can be really hard. And we managed to do this in some way, and we're going to see the details in the next, very next slide. And another limitation is the computational costs, because for Lagrangian-based method, typically it is very high. For me, that I work also with direct n-body simulations, the cost grows as n squared, where n is the number of particles, while for smoothed particle dynamics is slightly better, because you have that the cost grows as n logarithm of n, at least in the best cases. So let's now see what you can do with SPH. So you can simulate from the very large astronomical sizes like galaxies, because you have gases and star formation regions, which is pretty cool with SPH. I think that there are also people studying the cosmological simulation, making cosmological simulations with SPH. And also someone is doing SPH for studying mergers of neutron stars. So you can go up to stars and compact objects. But you can, of course, study planetary objects. That is what we are interested in today, mainly the volatile emission from surface structure. That is what I'm going to spend some time. But also post-impact plumes and the formation of transient atmospheres, as well as planetary disks and planet formation, like this paper, which was actually using SPH for studying giant planet formation. And then also you can study, I hope you are going to do this in the next future, that is comet jets and outbursts. But you can go also on human scales. So here I have a couple of examples that I'm going to show you, I hope. Let me set it too. So these are two examples of, let's say, engineering case when you are interested in knowing if a wave can interact with your boat or with a harbor. In the right case, it is a real harbor that is interacting with an anomalous wave. And so you may imagine how it is important to know for people living there if there is a large wave and what to do in that case, how to build their buildings to avoid this stuff. But also you can do something that may be more interesting, because you can even make cakes with SPH. So this is again an example of the project that I was using here for showing you, that is the dual physics that you can find on the web. So the next time that you make a cake, just run your SPH simulation, and then, only then, when you have your results, you can go and buy your ingredients and make the cake finally. So that was just for kidding. So now let's see the philosophy of smoothed particle dynamics. So imagine the cloud that I showed you before, and now you are interested in a generalical function A that is in a position that you can see there in green. So generally speaking, you can write it as an integration of the same quantity in an infinitesimal volume, where you have the Dirac delta in the integral. The first stuff that SPH do is a smoothing of the Dirac delta into a kernel function, which actually is an analytical function, which has this bell-shaped, and has a fixed domain determined by the so-called smoothing length h. So you can see that the particle identifying the position that you are interested in, so you would like to know the quantity A big in the a small a particle, and it is determined by the so-called neighbor particles that are those indicated in blue inside the domain of the kernel. And specifically then, since you have discrete stuff, you discretize your integral and you get actually summations. And what is doing the kernel? The kernel is actually weighting the property A, big A of the particle, the neighbor particles B, identified with a discrete subscript. So to visualize this, imagine that you are interested in the mass density. So instead of the big A, replace the density rho. So the fraction vanishes, and you simply get the summation over the neighbor particles multiplied by the kernel, which actually has the dimension of the number density. So this gives you the idea of the and the philosophy of multi-particle hydrodynamics. And with this scheme, you can write all the basic SPH equations from the physical ones. So let's see them. We have the continuity equation, which actually rules how the density evolves in time. And in the SPH formulation, you can write it like that one. So I want to stress that you have only summation of known quantities. And interesting stuff is that when you have derivatives with respect to space, they always go in the kernel derivatives. So since the kernel is an analytical function, its derivatives are analytical too. So you know them. And it's analytical. So you have each term inside the summation. You have only to make summation, and then eventually integrate over time to have the temporal evolution. Typically, for the density used, this other quantity, that is what I was introducing you before, that is, again, an average summation of the masses of the neighbors. Then you need, of course, the momentum equation that is ruling how your particles evolve in time. And here we have only a pressure gradient term, and the corresponding SPH equation is that one. For those interested in the details of the derivation, you can find several reviews by Monaghan. Its articles are pretty interesting, full of derivations, and you can find also that these equations, at least these are a bit simplified formulation, but those equations come all from Lagrangian function. And since they come from a Lagrangian function, they conserve energy. And that's why you need this kind of symmetric terms in the equations that you can see there in terms of the subscript, because without them, as it was in the very first formulation of SPH, you're not able to conserve well energy and momentum. So you need them. They actually come out from the derivation from a Lagrangian function. Then you would also like to follow the evolution of the energy. And we selected the thermokinetic energy, which is simply the summation of thermal and kinetic energy, and its corresponding SPH equation, that one. Again, you have summation of known quantities. And finally, you have an equation state, which is simply an ideal gas law, gamma index. So you now have a system of differential equations that you need to numerically integrate over time. This can be done with plenty of integrators. You will often have to determine your time step, your temporal step, according to the scientific case you are considering, so it needs to be adaptive. But another thing that is important in SPH that you need also an adaptive smoothing length, because to efficiently use SPH, you need enough number of neighbors inside your kernels. So you typically change the smoothing length of each particle according to some rules. So for those interested in these rules, we can discuss it later, but imagine that you would like enough particles to make a summation. The number is empirically determined, let's say, but it's around 60 particles, because you do not want too few particles, because otherwise you are subsampling your the space you are in, or you don't want too much particles also for computational reasons. And so finally, once you integrate it over time your equations, you get the temporal evolution of an hydrodynamical system. And on top of that, you can start adding your scientific effects, that is something beyond basic hydrodynamics. And this is what we are going to see for the emission of volatiles from planetary surface and surface structures. I will go into two examples of the Moon and Enceladus. But let's first see what are the motivation of studying volatile emission. So first, as any observable, they bring several insights. First, concerning the surface and subsurface physical conditions, as well as formation and evolution of the main body that you are interested in, and eventually its internal structure. But they can also trace past events like impacts and cryovolcanism or the formation of exospheres. But most importantly, they can also trace organic components. So this is fundamental for the search for biological life. This is what made Enceladus so interesting in the past and also nowadays, but also for the availability of materials for future settlements that can be interesting to know what kind of material you have on some object. And so now let's see what is our recipe for SPH. Again, the idea of making a cake, in this case, is not for cakes, it's for emission of volatiles. So I call it hybrid because, as I said, this basic hydrodynamics plus additional effects. So the basic hydrodynamics we already see. This is the set of equations that we use with a small modification, that is the presence of additional forces, external forces, like the main gravity of the object you are studying. It can also consider, for example, another object that, for example, can be Saturn for Enceladus or the Earth for the Moon. You can also imagine that that term can include additional forces like magnetic field if you have charged particles, or if you have an interaction, dynamical interaction between different components of your fluids, like if you have a dusty component and a vapor component, they typically interact via viscosity, and your term actually goes inside that G. And of course, you have also the energetic counterpart. But we're going to see this the next slides. So let's first see the first thing that you have to face. That is, you have solid boundaries, and you do not want that, of course, something like this, that your particles cross your boundaries, because this is not occurring. So the very early approach that you can use is mirroring those particles on top of the surface. So this can be easily done. You also have to mirror the velocity, and an idea can be that you mirror the component, the tangential component, and you actually can dump each component according to some laws. This is at least a very early approach, because a rigorous approach exists, that is to integrate the interaction of a macroscopic particle with a solid boundary, with each one with its own property, but you end up that the time scale for this interaction is extremely small with respect to the hydrodynamical time scale. And so you finish that you study this effect rather than volatile emission. So that's why you need an appropriate modeling for considering these finite microscopic processes into macroscopic ones, because you want to observe another phenomenon which has a greater time step. The same stands for phase transitions. So we are considering now the possible sublimation of icy grains into vapor and the deposition of vapor, mainly water, into icy grains. So we're not considering a free phase at the moment. And to do this, again, we use a statistical approach to determine the efficiency of such processes that actually we are measuring the probability of these processes to occur, to let the whole volume element transit from one state to another. And this can be improved somehow. So for those really interested in this stuff. We can discuss it later with Luca and Gianfranco, as was a few hours ago. And then you also want to consider that your solid boundaries may have a temperature. So imagine a very simple situation where you have, again, a flat surface, which its own temperature, even if it can be a function of position and time, and the same stands for the particle. So generally, you can have that your surface is colder or hotter than the particle, and you want to consider if your particle is able to deposit as if it was vapor according to the efficiency of conduction with respect to the dynamical interaction with the surface. So here again, the microscopic processes that you need to model somehow to understand if a macroscopic volume element is doing something, like depositing on the surface. And you can imagine that on the opposite case, when you have a hot surface, your particle can increase its energy, and if it was a descriptor of the icy grains component, it can eventually sublimate. And this comes with the solar radiation, because the first stuff that solar radiation do is giving you shadowed regions and illuminated regions. So you may expect that if you surround the moon with vapor, the vapor can stay in the vapor state in the illuminated regions, while the icy grains component should dominate in the shadowed ones, while you also have smaller temperatures over the surface. This again can be done by geometrical reasoning for the shadowed regions, and by considering the actual flux that each pseudoparticle, because we often call them pseudoparticles, the amount of flux each pseudoparticle see according to its optical depth. And finally, at least for the moment, there is the viscosity coupling and a possible dust component. Generally speaking, it is the interaction between a solid component, where solid means microscopic solid particles like icy grains, and a vapor component. So there is this viscosity that allows from the vapor transfer part of its momentum to the icy grains or the dusty component, and can accelerate it. But for the moment, this is a work in progress, because we are studying literature and understanding how to include this in our code. There are some hints, but what I think is the core of this, as well as the other processes, that we have to map microscopic processes into macroscopic ones. And the difficulty is often that if your microscopic process strongly depends on some physical quantities, microscopic physical quantities, like in this case, for example, the viscosity coupling strongly depends on the mass or the size of your grains. So you need to understand how to map this into pseudoparticle properties. And Luca is doing a very good job in the last weeks. So again, if you want to know the details and discuss with us, we can wait up the end of the seminar. And now let's see some preliminary results. So first, I simulated a post-impact plume over the moon surface. So let's see rapidly the scientific background. For those who don't know, there is an increasing evidence of water ice on the moon from different instruments. We have an amount of ice in the permanent satellite regions, mainly in the polar caps, where we see ice inside those craters. And there also is a day-night variability between the surface and the water content in the exosphere. At least it is primarily suspected. And without going into the details of the observation, because I'm not an expert in this field, the idea is that this material can come from impacts or cometary objects over the surface of the moon. And so, in our case, it was a test for the process that we considered, and we actually set our initial conditions immediately after the impact. So simulating a fireball, assuming it is spherical, it is at the surface, has initial high temperature, and it is mainly composed of water vapor and at saturated conditions. And this is what you obtain. I hope the simulation is going to start from the beginning. Okay. So you have in orange and yellow the gas component, while the ice component, which is in green and blue, and the sun is coming from the left, and the simulation time is fortunately only 1 hour and a half, so you are not able to see the rotation actually. And you can see how much the ice component is actually present only in the shadowed regions, at least the flying one, because if you go and see the deposited material, you get that at poles, the deposition of ice is efficient, even in the illuminated region, also some real sublimation, of course. So what you understand from this is that there is a not negligible amount of matter that can deposit over the moon. You can produce a transit atmosphere that may live some time. Gianfranco told me that he has made some simulations about that. So for those again interested in such stuff, we can discuss it with him the next time. But as I said, this was just a test because our final goal, at least for me, in my view, is simulating Enceladus plumes, because we have the Cassini observations that give us a lot of information that can allow us to constrain the free parameters of such models as well as initial conditions, because remember that those numerical methods all need some parameters to determine the initial conditions actually. So let's see again here also the scientific background. I mentioned the Cassini mission because we know from it that we have supersonic jets from gassing from several fractures along the tiger stripes that are those straight, more or less straight lines in the south pole of Enceladus. And these jets are mainly composed of water vapor and icy grains, but also organic components. And this is what brings them to be really interesting. The velocities are estimated of several hundreds of meters per second, and the mass loss is more or less, the overall is from 100 to 1000 kilograms per second. And this material is actually feeding in the Saturn A ring. So there is some kind of variability in this process, not only due to the different measurements, but probably also due to the mechanism itself of the mission. So we start from the very beginning, since we are building actually our model, and our initial condition first consider a single fracture that has a geometry determined by the observations, and it has an initially amount of only water vapor, and is filled with this amount. So we are not living in a fraction, so you are going to see a mass loss event rather than a continuous mass loss. And we set it at the triple point of water because we are thinking in terms of where this material comes from, that is the subsurface ocean, because at South Pole we expect that the thickness of the crust is 5 kilometers. And this is actually what we, just to start from the beginning. This again, the colors are the same. This is the result when you start to consider the several effects that I mentioned before. As you can see, there is an amount of material that is deposited on the surface, which may be interesting, but also you are not able to see the content of ice in the plume. And this suggests that probably the considered initial conditions are not properly well, or we are missing something. And in particular, we are missing an energy sink, that is the interaction with the fracture walls in the thermal interactions. Because you may imagine that you have subsurface ocean at triple point of water, and the top of the Enceladus surface is at 85 Kelvin. You have an important gradient of temperature, and the conduction can be efficient in that inside the fracture. And here you have only that energy sink somehow for the vapor emitters. And the picture should change with this effect, so we are not considering at the moment. This is the amount of material deposited. As I said, it is non-negligible. although you may imagine that this can be different if you go again, you simulate more time, because we see only 60 seconds, because the time step for the mass loss event is like 10 seconds. So we may have to simulate a continuous emission or simulate larger fractures that have a more amount of material. So in conclusion, I hope I convinced you that to perform realistic simulations, we need to include several processes, and we need appropriate modeling for them. And modeling that is simple and that is fast, in a sense, in computational sense, because the microscopic processes are highly affect the outputs that we have. And like I was saying, the thermal interaction with boundaries can be very important in the outcomes that you obtain. And this is matter of improvement. As you said, these are preliminary results. We are working on this. If you are interested, we can also work together, because the final goal of our work is to produce a tool to be used in different contexts. So with the perspectives that are actually not only related to the moon and Enceladus, but also to different objects like comets, planets, and other moons, like it is in Europa, which seems to be to have the same plumes like Enceladus, but it has a gravity closer to that of the moon. So it may be more interesting to study these effects in such a reference. And so that was all. I was running because the time is still there. And I leave you with the last slide of the missions, my contacts, and the website. And thank you for your attention.
Matteo, for the nice seminar. If there are any questions, I will just ask to those that are online eventually to raise their hand so I can manage the order of the questions. And I will start with the people that are on the floor. So, any question for Matteo? Vai Alessandro.
Inglese?
Yes.
Devo parlare...
No, c'è il microfono, quindi there is the microphone, so it should be clear for everyone.
Matteo, so did you consider also to make some more complex geometry, for example, making the body rotating while you have the emission?
Yeah, I think these are two questions, because the first is related to the fact that for having more complex geometries, you need probably to use SPH itself to draw your fracture. So, because we are now, our fractures are surfaces, analytical surfaces. So to make it efficient, you would like to pass to SPH generation of particles, so you can make them as you like. And then you have to face the interaction between your particles and those SPH solid boundaries particles, which can be hard, but can be done. There are people working on this, so it can be done. And then concerning the rotation, actually, at the moment, what is rotating is only the solar radiation. So you have that you are in the reference that is solid to the object, and actually what is rotating is the universe, which is strange, but for you the universe at the moment is only the sun. So you can simply rotate the vector of the solar radiation. You do not see it because you have 1 hour and a half, but we make longer simulation, we can see this. Or we change the period of rotation. Okay. We see.
And another point, for the future, how difficult it is to include also diffusion? So for example, on Mars, even if it is thin, you have to consider an atmosphere. So if you are simulating a plum or an emission, a gas emission, you have to consider diffusion, winds, or at least an atmosphere that gives diffusion.
Yeah.
Is diffusion difficult to implement there, or is it just a matter of trimming the equation?
Actually, in the SPH approach, you can introduce whatever equation you like. But of course, as I said before, if you must be careful, because if you introduce some equation that has a time scale which is extremely small, you end up to study one phenomenon instead of another. For the case of an atmosphere, probably including an O'Learyan approach would be better, because otherwise you are limited or introducing an atmosphere and a fixed area, because otherwise you have to consider the whole planet, which is not interesting if you are interested only in the specific location. So once you select a given volume, let's say, of the atmosphere, maybe O'Learyan methods for that are better. But we can also work in merging those methods, like you speak O'Learyan methods with SPH methods. Mm-hmm. This is one of the other interesting parts. Also includes the interaction with the surfaces, so you can use O'Learyan methods for the surface and SPH for the transient events.
So basically, you can mix, for example, a finite element and a SPH.
Yeah, there are people working on this.
Okay,
it's pretty hard. I think it's pretty hard, but we can manage to do this in the future. I don't know the time scale for this.
And the last point, did you ever thought about simulating, beside the cake, of course, but simulating like a real small plum in the lab with the SPH?
I'm sorry, I don't know.
A small gas emission, let's say, simulating a gas diffusion in a lab with numerical models.
In a lab, you are seeing
in a square, or
in a
like
box.
going at Campbell Gray, let's say.
Well, actually, yes, but it was a test in 2 dimensions, so it was just to at the very beginning. I was testing it as stuff. Yes.
Okay. Thanks, Matteo. Good job.
I have one curiosity. There are yet some models using this SPH approach for the fracture, fracture or something like that.
As far as I know, there are not models using SPH. Okay. There are models solving numerical equations, but they are typically limited to several assumptions, like you solve one-dimensional equations, and you find a way to change the dimension, the section of your fracture. And I think this must be considered for comparison with our model. Maybe in the work that we are preparing, we have to discuss this. But I think that it can be more interesting in simulating a 3-dimensional case, which is more realistic, like, as I said before, making a fracture that is made from our models for the surface, rather than assuming actually that the dimensions of the fracture is random, as someone is doing, between some extremes of the section. But generally, we have to face with these other models, which are not SPH models, are more or less the numerical resolution of equations for hydrodynamics in 1 dimension, so it's easier, and but are not in the SPH framework.
On the Celadus case, maybe I missed it. You see the formation of ice grains within the blooms, or just on the material which is deposited to the surface? Because Celadus blooms with the ring, this thermos diffuse ring made up of microscopic submicron icy grains. So you see grains escaping through them.
that's what I was trying to say, probably too fast. And in that simulation, you'll not see icy grains. You start to see them at the beginning, because actually your plume is as an optical depth that is high enough to prevent the solar radiation heat up your plume. What I think is that the probability of forming icy grains in the free expansion space is less than the probability of producing icy grains inside the fraction. So probably what we see are icy grains accelerated inside the fracture from the gas component, which are formed there. So I'm making some tests changing the initial fraction of icy grains. The first time I was introducing icy grains at the beginning, and actually picture changed a lot. I'm not still confident about the results that we have found, but you see an enormous amount of an important fraction of ice in the plume, and which has a large variability. So we expect, if I'm not wrong, around 30% or 75% of icy grains in the plume. But I think this can be strongly altered by what occurs inside the fraction, because there you do not have actually the energy source of the sun. You only have energy sinks.
Once you form these grains there, then you can let them travel and survive.
Yes.
Question like this, with these plates. Can you consider using this method for simulating small scale events like meteorites acting on the surface and follow the dynamics of the dust plates, create or of dust?
Yes, but as I try to stress, our particles are macroscopic descriptor of fluids. So when you start introducing dust, you have to consider that dust has a size distribution, etc. So if you introduce only one component of the dust, you are fixed to consider a fixed size, average size, more or less. And if you do so, you lost some interesting information, that is where some size particles arrive, where the property as function of size, as function of mass of these particles. And we can manage to do this by including different components, yes, but you never end up by studying a single grain. So you have always a descriptor of a fluid of that kind of grains.
That would be representative of the
Yes, they should be representative. Otherwise, you cannot use a model like this. Yeah, you have to be in the limit that this polymer element is a good descriptor of your component. Yes, in principle, you can do this.